Okay, well, welcome to our second lecture, and I've thought I'd begin this by showing you how to log into our newly created Canvas page where you can discover all of the course materials that you'll need. So if you go to Resources on the college's homepage and go to eCampus Canvas Login and follow the link, it'll bring up a dialog box to log into Canvas. So you put your student number in, and it will bring you to a page that will, under courses, hopefully have our chemistry course. So mine's a little bit different because I've been using it for a little while, but if you go under courses, you should find that you have Chem 121 added there. So follow that course. Now once this comes up, I'm going to have a look at this in student mode, so it won't look quite like this for you. So I'm just going to quickly do that. So student view over here. Okay, and so now we'll be looking at exactly what you will see when you select Chem 121 from your courses menu up here. So you select Chem 121 and the page will look like this. Now I sent you a notice that in the announcements here, and it directs you to, it's a little bit slow, the connection at the moment, so I apologize for that. It sends you to this page, and if you load that up, it'll give you directions for accessing a online tutorial on how to use Canvas. You know, you can or can't, it's up to you whether you use that tutorial or not. Canvas is fairly intuitive, and I've set the web page up as simply as possible. So going back home again, let's have a look at what's on the home page. It's being a little annoyingly slow. So it has basic details about the class in the top there, and then we have the syllabus. You click that, it will bring up a web page with the syllabus that you can download, the lecture notes, a link that takes you directly to our YouTube channel. It opens in a separate tab. It takes you to my channel for this class. Here it is, and you can download lecture notes there, or course videos there. And then the other nice thing that I set up is a link that takes you directly to OWL, so you don't have to go through so much hassle. It skips all that step of selecting the correct book, and then all you have to do is either register if you haven't yet, or log in. So about 30 people have registered for OWL at the moment, and I imagine a few more will before too long. So there you are, you can log into OWL, and it takes you directly to our page from there. Okay, so similarly, here we are. The YouTube channel is there, and slowly that will populate with videos. Alright, so lecture notes is probably the thing that you'll want most frequently, and you follow there, and hopefully soon it will pop up our lecture notes. So I'm going to open that guy. Would like to open it, and it's going to take a little while, but it should pop up the lecture notes in PowerPoint. So the other interesting, the other menu of interest on our web page things that are in here, we have the lab reports. So in the lab reports are the list of documents that you use to report your lab results. So in week 1, I printed out and gave to you the document that you needed to complete your lab report. For the remaining weeks of the quarter, it's your responsibility in the time after the lab to print out the required form that you need to fill in for presenting your lab report. So if you recall, our labs are due exactly 1 week after you did the exercise. So I would recommend that you know that you've got lab 2 coming up, separation, so download and print that form off now if you have this lab next Monday or Wednesday. So that's sort of an overview of the website. People are working through OWL, people are working through Canvas. It might take a little time, but I'm certain that we'll get there. So now we're going to go back to chemistry content. So here we are. So we're looking at the final 5 sections of chapter 1. We're going to look at the classification of matter into elements and compounds. Previously we had looked at the classification of matter into pure substances and mixtures, and we noted that mixtures could be divided into either homogeneous mixtures or heterogeneous mixtures. Well, now we're going to look at how we can divide pure substances into either elements or compounds. We're going to talk a little bit about the discovery of the elements and the discovery of artificial elements and their abundance across the entire universe, across the human realm, and within our bodies, just briefly. Then we're going to do a section where we talk about how elements are named and how we give them symbols. We'll then move on and look at the distinction between atoms and molecules, and finally we'll look at how we can represent the ratio of atoms and the atom types that are present in molecules using chemical formulas. So this is where we left off last lecture. We said that matter was everything that had mass and had occupied space, had a volume. That was matter. If it didn't have that quality, it was something other than matter, and in particular we drew a distinction. We said that energy is not matter because it does not have mass and it doesn't occupy space. So matter, we said, could be divided into mixtures, and mixtures have variable composition. For example, a solution could be weak or it could be strong. We could have a very salty solution of salt and water, or we could have a very dilute solution of salt and water. The components in mixtures, they're just several pure substances combined together, but they retain their characteristic properties. And one of the key characteristics of mixtures is that they can be separated into pure substances by physical methods: filtration, distillation, or even just manually sorting the substances out. So, mixtures can be classified either as homogeneous or heterogeneous. Homogeneous mixtures have the same composition throughout the entire mixture, and the components are indistinguishable. Homogeneous mixtures are always all one phase. Heterogeneous mixtures do not have the same composition throughout the entire mixture. A sample of one region may be different in composition to a sample of another region of the mixture. Sometimes heterogeneous mixtures involve substances that are in different phases. But the key characteristic of a heterogeneous mixture is that the components are certainly distinguishable. You can recognize different components in the mixture. Pure substances, unlike mixtures, have a fixed composition, and you cannot separate them into simpler substances by physical methods. That's because there's only one substance present. There's nothing to separate. The only way that we can break down a pure substance is through a chemical method. We could possibly separate it into simpler particles, but that would result in an alteration of the composition of the sample. So, in modern chemistry, we take an atomistic view of matter. That is, that we consider matter as being composed of particles that are called atoms that are indivisible by either physical or chemical methods. And this was an idea that the first sort of formulation of this idea is generally attributed to the Greek philosopher Democritus. Now, many people of his era, many scholars of his times, considered that this was an incorrect view and that there was in fact no limit to the subdivision of matter, that there was no fundamental particles, that atoms simply didn't exist, and that there was no limit to which you could divide matter into smaller and smaller and smaller pieces. So, elements are substances, pure substances made up of identical atoms. So there are 118 known kinds of elements, and most of these have been discovered from the 1700s onwards. Each element has its own symbol. The first character in an atom symbol is an uppercase letter, but most atoms have a second character in their symbol, which is always a lowercase letter. Perhaps the material made of a single type of atom that you are most familiar with, or you've probably seen the most frequently, is aluminum foil. Aluminum foil is a very, very pure form, and it contains nothing but aluminum atoms. So, in addition to its symbol, each element has a name. And for 11 of the elements, the names and the symbols are very different. So 10 of those elements have 10 elements have names that are derived from Latin. So obviously the English name and the symbol will be different. And one element has a symbol, which is, this element is tungsten, which is derived from German. So we can see this, the symbol for potassium is K, and it has no obvious relationship to the English name. The symbol for tungsten is W. It comes from the German for Wolfram. And then the symbol for sodium is Na, and that comes from the Latin for natrium. So in the front cover of your textbook, you have a table somewhat similar to this one that lists elements' names and also their symbols. Now, you do not need to remember all of these names and all of these symbols. I will always provide you with a periodic table that lists both the names and the symbols of the elements if you need it. So 88 of the known elements exist naturally, that is, they are just naturally in the universe or on our planet. But 30 have been produced in the laboratory, and these are produced generally in particle accelerators by the high energy impact of stable known natural elements with high energy particles. So these so-called synthetic elements, they're all very radioactive and they exist only for short periods of time. So what are the most abundant elements in our universe? Well, most of the matter in our universe is helium and hydrogen. Most atom types in our universe are hydrogen atoms or helium atoms. In fact, our universe is approximately 91% hydrogen and 9% helium, with less than 0.1% other types of atoms. So how do we know this? Well, we know this because we can examine the light that comes from stars. And the light that is emitted from a gas when it is glowing is characteristic of the atom types contained within that gas. So you've probably all heard of or seen neon tubes, and neon tubes are filled with neon gas, and when those tubes are energized, it gives a characteristic pink glow, and this is the characteristic pink glow of the element neon. Similarly, you may have seen often at intersections they have the bright yellow street lights. Well, that's because the tubes that they use in those lights are full of sodium. So that's a characteristic emission of sodium. So by examining the light that is coming from space, we can determine the composition of the relative abundance of elements in the universe. So if we look at the outer layer of the Earth where we live, that is the solid part of that is what we call the crust, and then the gaseous part of that is the atmosphere, and then the waters being the liquid part. We see that most of the matter in the realm where we live is oxygen and silicon. 80% of that matter is either comprised of oxygen atoms or silicon atoms, with 60% being oxygen atoms and about 20% being silicon atoms. Then of the remaining matter, it's divided across 6 other elements, namely aluminum, hydrogen, calcium, magnesium, iron and sodium, with only 1% of other trace elements present. So the composition of the place where we live is actually not very representative of the universe at large. If we look a little bit closer and we look at what makes up our actual bodies, we see that it is very different from even the Earth or from the universe in general. And what we find is that humans are comprised mostly of hydrogen and oxygen, and you've probably heard this, that we are mostly water. And so about 60% of the atoms in our bodies are hydrogen atoms, 25 to 26% are oxygen atoms, and then the remainder is distributed mostly between carbon with about 11% and nitrogen with about 2.4%, and only 0.7% of other trace elements. So that's interesting, because we're saying we are mostly hydrogen and oxygen, but the region in which we live is mostly silicon and oxygen. So what does that tell us? What does that tell us about how our bodies function? So yes, the distribution of elements within us is very different from the elements that are in the Earth's outer layer where we live. So what does that say about how our bodies absorb nutrients? What this means is that our bodies absorb nutrients selectively. Some of the elements that are in our environment we don't absorb, and some of them we absorb preferentially over others. That is, we have a preference for absorbing oxygen and hydrogen over silicon. While silicon is very abundant in the Earth's outer layers, we have almost none of it within our bodies. So we've talked extensively about elements. The other class of pure substances are compounds, and a compound is 2 or more different atoms chemically bound together. And now, because these atoms are chemically bound together, we can't separate them by physical means. So an alternative definition of a compound is that it's the limit of physical subdivision. You can't divide the atoms that make up a compound using a physical method, like with a knife or some other physical way of cutting things up. So the elements that are present in a compound are always there in the same ratio for a given compound. For example, a sample of ammonia, which has the formula NH3, and we'll talk a little more about formulas later, will always have 3 hydrogen atoms for every nitrogen atom. Always. If it doesn't have that ratio of nitrogen to hydrogen, then it's not ammonia. So the elements present in a compound are always there in the same ratio for a given compound. So now we can look at our distribution of matter in a little bit more detail. So the first question when we have a sample of matter that we may ask is, can it be physically separated? Can the components be physically separated? And if the answer is yes, then we have a mixture. So we now know that we have a mixture, and we ask ourselves, is the composition uniform? Does a sample from one region of the sample of matter have the same composition as a sample from another region? And if the answer is yes, then we have a homogeneous mixture. And if the answer is no, then we have a heterogeneous mixture. Now, if our sample of matter cannot be separated into multiple components by a physical process, then we don't have a mixture, we have a pure substance. And then we have to ask ourselves, can it be chemically decomposed into different atom types? And if the answer is no, then we have an element, and an element cannot be chemically decomposed into different atom types because there's only one atom type present. However, if we can chemically decompose our pure substance into multiple atom types, then we must have a compound. So now we start talking about, in even more detail, about pure substances. And now we're going to talk about molecules. And what a molecule is two or more atoms chemically bound together. Now this may be atoms of the same type, or it may be atoms that are of different types. And we name molecules in a variety of different ways. A diatomic molecule is a molecule composed of two atoms, and I've used what's known as a ball and stick model to indicate that here. Here's one atom represented by this ball, here's the stick that joins the two atoms, and here is the second atom. A triatomic molecule is a molecule composed of three atoms. Here we have one atom, two atom, three atoms. Now when we have three or more atoms, there are a variety of molecular shapes that are possible. In this scenario, I'm showing the atoms joined together in a V shape, but I could have equally shown them joined together 1, 2, 3 in a row. And so there's a variety of shapes that are possible for molecules. A molecule composed of four atoms is called a tetraatomic molecule. A molecule that is composed of five atoms is called a pentaatomic molecule. But typically, once we get beyond three atoms, we will just refer to a molecule as being polyatomic, being a polyatomic molecule, which means made of many atoms. So the atoms that are in molecules, as we mentioned before, cannot be separated by physical processes. This is a chemical bond that is joining these atom types and can only be broken by chemical processes. So for this reason, we say that a molecule is the limit of physical subdivision. So 7 of the elements, remember elements are substances made of a single atom type, are found in nature as diatomic molecules. And we can one of the ways that we can remember these is that 6 of them, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, form a 7 on the periodic table. And the other diatomic element is hydrogen. So hydrogen is present in nature as H2 molecules. Nitrogen is present in nature as N2 molecules. So we can define molecules as being either homoatomic or heteroatomic. Homoatomic molecules contain atoms of the same type. An example would be an oxygen molecule. Oxygen is a diatomic element composed of molecules comprising 2 oxygen atoms. The other class of way of classifying molecules is as heteroatomic. Hetero means that there is more than one atom type present. So here I have a water molecule. This large atom here is an oxygen atom, and these 2 smaller atoms here are hydrogen atoms, and so we would classify this molecule as a heteroatomic molecule because there are 2 different atom types. This in fact would be a heteroatomic triatomic molecule because there's 3 atoms present. So the final topic that we're going to talk about is how we can use chemical formulas to indicate the type and number of atoms present in a compound. So when we write a chemical formula, we use element symbols to list the types of atoms present. So for every atom type present, we write down the element symbol one after the other. We then add what are called numerical subscripts to indicate the number of each atom type. However, it's important to recognize that if there is only one atom type present, then no number is written. So for example, water is comprised of hydrogen and oxygen atoms, and there are 2 hydrogen atoms for every 1 oxygen atom. So we write down hydrogen and oxygen, and then we add the subscript of 2 to the hydrogen. Now there are a few caveats to remember. Firstly, capitalization is important. You need to write the correct symbols for the elements, including the correct capitalization. For example, C, uppercase O indicates the compound carbon monoxide, which has 1 carbon for every 1 oxygen atom in its molecules. Whereas the formula, or the symbol in fact, for cobalt is an uppercase C followed by a lowercase o. This indicates the element cobalt. So we have to be very cautious there that we don't get our capitalization wrong. Sometimes we group atoms using parentheses. So this compound here is called barium nitrate. And you can see that I've got this group of atoms, NO3, within parentheses, and then there is a subscript 2. And this indicates that there is 2 of everything that is in parentheses. So in this compound, there are 2 nitrogen atoms, 2 times 1, and 6 oxygen atoms, 2 times 3, for every 1 barium atom. Okay, so it gets a little bit confusing, but we'll do plenty of practice. So for homework, you need to read through the remainder of the chapter. I have our problems that are scheduled to complete between now and Monday's class. If you have access to our, please complete those problems. And then you should do as many problems from the book as you can, and the sections that we have just covered are dealt with in problems 1.29 through 1.88. Thank you.